Thank you very much, Jan. My name is Shuji Tanaka from Tohoku University, Sendai, Japan. Okay, today I will talk integration method, heterogeneous integration method. What is a heterogeneous integration? This is the integration of the different kind of components, for example, MEMS and IC and SAW device. And also the integration of a different kind of materials, silicon and piezoelectric crystal. This is useful. Why it is this? I will explain later. But it is. It's automatically going. Why?
Usually you can use this instead. Down.
I didn't use this. Okay.
Okay.
So due to the process incompatibility or material contamination, this is an example of the merit of heterointegration. This slide, this doesn't work well. This slide compares two transduction methods, electrostatic one and the piezoelectric one. They are the same cantilever, but piezoelectric actuation can drive the same structure at much lower driving voltage, 10 times lower than that of the electrostatic actuation. So to use a piezoelectric material is advantageous. However, there's a problem. You know that PZT, the typical piezoelectric material, is difficult to deposit on the LSI because the position temperature is as high as 600 degrees C. It's too high for the standard CMOS. So what I did is to transfer the PZT structure to the LSI. The PZT structure was made on the silicon wafer and then patterned into the cantilever structure. The CMOS was fabricated in a CMOS foundry, and they are bonded by the bonding polymer. The blue part is the bonding polymer, and then the silicon wafer is removed. Finally, the PZT cantilever structure was transferred from the silicon wafer to the CMOS wafer. And then the PZT structure and LSI was connected by the gold electroplating, and finally the blue part, the polymer, was removed to release the PZT actuator. And this kind of method is versatile, can be applied to the different kind of materials. This is one example. We made the BST Varactor on the 0.18 micron CMOS power amplifier. And it works as a tunable amplifier. So BST is also the ferroelectric material which is deposited at very high temperature. So using the same kind of method, we transfer the BST film from the silicon wafer to this CMOS wafer, and then fabricated this amplifier. This is another example. This is a bioelectrochemical sensor array. 20 by 20 diamond-based electrochemical sensor was fabricated on the LSI. Why we use the diamond electrode? This is because the diamond is one of the best material for the electrochemical detection. Here you can see the potential window. This is a potential, and this is current. Compared to the noble metal like gold, carbon material has a much wider potential window. This means carbon electrode can detect many kinds of chemicals with different potentials. And also, you can see the intrinsic noise of the carbon material is lower than that of the gold electrode. The same fabrication method was used. The diamond was deposited on silicon wafer at the plasma CVD. 800 degrees C was the deposition temperature. And this was patterned. And then LSI is again fabricated in a CMOS foundry. They were bonded together using the BCB. BCB is the polymer. And then silicon was removed. Finally, the diamond electrode and CMOS was connected by gold chrome metallization. And then device was fabricated. And this is a fabricated device. This is CMOS, and on the CMOS wafer, we made the diamond electrode, and this is the individual electrode. There are 20 by 20 array of the electrode. And this is one of the demonstration. We dropped the small droplet of the histamine on the device. And the diffusion of the histamine was visualized like this. The potential of the detection of histamine is 1.4 volt versus silver chloride electrode. This is quite high potential. It is difficult to detect the histamine using the conventional metal electrode. We are now using this kind of system, for example, to screening screening the chemicals because there are many cells. The most commercially successful MEMS is the inertia sensor, as you know. This is a gyroscope which is installed in the Toyota Lexus. It's a luxury car. This was developed in Tohoku University, our university, and now commercialized. And this is used for the vehicle stability control. And this is acceleration sensor, and these kind of sensors are used also in Nintendo. I don't play in Nintendo, but some of you that play in Nintendo maybe. The size of the sensor is now decreasing. The latest 3-axis MEMS sensor is just 1.2 by 1.2 millimeter. It's quite small. The 3-axis. Bosch released such kind of very small sensors. This is a combo sensor. A combo sensor is a combination of the different kind of sensors. The 3-axis accelerometer, 3-axis gyroscope, and 3-axis e-compass. There are 3 major companies, ST, Bosch, and InvenSense. If we compare 3 combo sensors, the InvenSense one has the smallest footprint, just 3 millimeter by 3 millimeter. And then, and also, this device uses just 2 dyes. Other companies are using the 5 dyes. So this is smaller. Why they can make the device too small? Because this is a hetero-integration technology. This is a fabrication method of the integrated MEMS sensor, which is used by the InvenSense. They use the cavity SOI wafer. This is a SOI wafer, but has a cavity inside. And on this, the MEMS sensor, for example, the gyroscope, is fabricated. And this is a CMOS ASIC, and they are bonded by the aluminum-germanium eutectic bonding at 450 degrees C. Of course, they are electrically connected, and simultaneously, inside the cavity is sealed in vacuum. This is very important. No MEMS sensor works very well without this hermetic packaging. So the packaging is necessary, but by this method, the integration and the packaging can be simultaneously achieved. This is very important. And this kind of the approach was applied to the F-bar, integrated F-bar oscillator by Rich. This is also clever solutions. However, there's one problem. This method is only useful when the two die has a similar size. If the MEMS and the ASIC has a similar die size, it's okay. But either of them has a much larger than others, the useless part is created. For example, in this example, the MEMS is much smaller than the ASIC, and this part on the MEMS wafer is completely useless. This is a problem. So to solve this problem, we developed this kind of selective dye transfer technology. The MEMS was fabricated on the wafer, and it is supported by the glass wafer with polymer adhesive. And ASIC, this is an ASIC wafer, and bonding part made of the, in this case, gold was fabricated. They were bonded by thermal compression, but after that, only a selected die is debonded from the support wafer and transferred to the LSR wafer. And this wafer, this die is integrated with this one, and also inside was sealed. Of course, other chip still on the support glass wafer can be used to the next LSI wafer. For bonding, we use the gold bonding because this is done by at a low temperature. The problem is the unevenness of the height on the LSI. So we first electroplated the gold on the LSI, and the surface was planarized by the fly cutting using the diamond bead. And finally, we can obtain such kind of flat surface for bonding. This is the fly cutting is useful for planarization, but also useful to make the gold grain smaller. This is as deposited gold, and this is after fly cut. You can see the grain size is fractionated. This is important for the low temperature bonding. And what we integrated is the tioudent F-bar and the CMOS, bi-CMOS sustaining amplifier made by the AKM. Two devices were integrated in a wafer level, as I explained, and this is a fabricated device. The wafer, LSR wafer, is come from the multi-project shuttle wafer. So our part is only red, this red region. And four oscillator was successfully fabricated. And this works very well. You can see the carrier frequency is 2 gigahertz, and the low phase noise was observed. This kind of method can be applied to the different kind of materials. In this case, lithium niobate surface acoustic resonator was integrated on the CMOS sustaining amplifier. The difficulty is, of course, the mismatch of thermal expansion. The coefficient of the thermal expansion is quite different between two materials. So we need to integrate, of course, at low temperature. The process is similar as I explained. The lithium niobate wafer was supported by silicon wafer by UV polymer at low temperature. The lithium niobate was thinned down to about 10 micron in this case by polishing. And then by standard method, the SAW device was fabricated, and the each die was separated by the half dicing. This process is very important. After half dicing, this wafer almost shows the similar thermal expansion coefficient than, with that of the silicon. So we can integrate the device using the gold-gold bonding. Gold-gold bonding. The bonding was done at 150 degrees C. And then by dissolving the sacrificial layer, in this case, germanium is the sacrificial layer, we separate the silicon wafer from the lithium niobate simplate. This works well, and the carrier frequency is 500 megahertz. And again, the low phase noise was observed. The bonding is a key process. We developed our own wafer bonder. This is a through vacuum wafer bonder. The three chambers are integrated and connected in vacuum. This is an alignment chamber, and both sides. This side, there is a treatment chamber. Sometimes we use the copper. Copper has an oxidation problem, so such kind of oxidation must be removed. But we cannot expose the sample to the air after cleaning. So they are connected in vacuum, and this is a bonding chamber. As we can to use a different size of the wafer. Many pistons, about 100 pistons, are installed at the back side of the bonding stage. We fabricated this one, and it is now commercially available. And sometimes we want to integrate a device by the chip-to-wafer manner. This is almost similar to the conventional flip chip bonder. But the important point is MEMS and resonating device must be hermetically packaged, hopefully in vacuum. So the conventional flip chip bonder cannot be used. So this flip chip bonder works in vacuum. In the vacuum environment, we cannot use the vacuum pin set. So the chip is handled like tweezers. And this is flipped and then bonded to the wafer. And this is our device. And this is the demonstration. This is the FBAR chip. And then this was aligned using the image processing and finally bonded. The last example is the tunable filter. We fabricated a tunable filter for the TV white space cognitive radio. The digital TV band is from the 470 megahertz to the 700 megahertz. There are 40 channels of the 6 megahertz channel. However, all 40 channels are not used. In Sendai is rural, so just we are using 6 channels. And the neighboring city, Ishinomaki, the neighboring city, it was heavily damaged by the tsunami the 4 years before, is also using just 6 channels. So other channels are completely open, and we can use this open channel, which is called the white space, for the other purpose, like Wi-Fi. But this is not easy for the filter point of view. We need to select different channels depending on the cities, and sometimes depending on the place, the outside or the inside the building. Of course, we can prepare the lot of filters and the switches, but it is not good for the cost and size point of view. So what we developed is the tunable filter. The configuration is like this. This is a radar filter, but to each resonator, surface acoustic resonator, there is a Varactors. If we change the capacitance of the Varactor, we can tune the passband. In this case, the passband width was tuned by changing the capacitance. This was actually designed by Professor Hashimoto in Chiba University. We can make this kind of device on the printed circuit board, of course, by soldering. but it is quite large, and of course, completely useless in your smartphone. We need to make it very, very small, hopefully the one chip. So what we did first is to use a MEMS Varactors. We made a MEMS air gap Varactor on the lithium niobate wafer. It partially works, but not very good. The biggest problem is the size of the air gap capacitor. The size is several hundred micron. It's sometimes 1 millimeter by 1 millimeter. It is too large. And we need 10 Varactors, so the device becomes too large. So the second choice we did is to use the BST Varactor again. The BST is changed its dielectric constant by the bias voltage like this. So if we can make the BST Varactor on the lithium tantalate wafer, it can be used. But the BST is deposited at very high temperature, as I described. So it is impossible to deposit a good BST on the lithium tantalate wafer. Lithium tantalate has a strong pyroelectric effect, and it's easy to crack if you increase the temperature. So the BST was deposited on the sapphire wafer, and then patterned into the capacitor. On the other hand, on the lithium tantalate wafer, the surface acoustic resonator was fabricated in a standard manner. And they were bonded using the metal-metal bonding. And then this sapphire wafer was separated from the lithium tantalate wafer. And at that time, this film was transferred from the sapphire wafer to the lithium tantalate wafer, and then finally we metallized to connect the IDT and the BST Varactor. Of course, the key point is how to transfer the BST from the sapphire to the lithium tantalate wafer. Our solution is to use a laser-assisted peeling method. The BST pattern was irradiated with the laser from the backside of the sapphire wafer. By this irradiation, the adhesion between the BST and the platinum was weakened. So after bonding, bonding was done at 150 degrees C, and then sapphire was mechanically removed. It's easy to remove. And fortunately, this structure was transferred to the lithium tantalate wafer. And then we made the electrode. Of course, to increase the yield of transfer, we optimize many parameters. Of course, the laser power, and the other important point, the layout of the device, the BST. For bonding, the uniform force must be applied to each Varactor. So using the FEM simulation, we optimize the position of the dummy BST wafers. And finally, 100% transfer yield was achieved. This is a single resonator and a single Varactor. As theory teaches, the anti-resonance frequency changed by applying the bias voltage to the Varactors. You can see clearly the anti-resonance frequency is changing. And this is the final device. The final device, we need 10 surface acoustic resonator and 10 BST Varactors. So the yield of the transfer is very, very important. Almost must be 100%. Otherwise, even the patient student cannot complete this device. So we successfully fabricated this one. And this works good. This is a measured characteristic. By applying the voltage, the pass bandwidth changed, and this is the simulation. Of course, the performance is is worse compared to the designed one, but it works almost as designed. And we installed our filter, tunable filter, into the TV white space cognitive radio system developed by the NICT in Japan. These terminals are connected in the TV band and through our filter. Our filter is here. And if we request the home page connection of our university, we can successfully see our top page of Tohoku University. Okay, today I introduced the integration technology related to the acoustic wave device. Using this kind of technology, I believe there is a lot of room to create a new kind of devices. And this kind of technology is very useful to minimize the size of the device, and to minimize the size of the device, achieve the, of course, low cost. Okay, I want to thank to the all laboratory members. This work was mainly done Professor Kadota and Professor Hirano. They were the member of our laboratory. And of course, I need to thank to our partners, Murata, Taiyo Yuden, AKM, Professor Hashimoto, and NICT Kyushu University. Thank you very much.